Hey guys, Mr. Bowman here. We're looking at 1.6 geometry, and this exam's a bit more useful to go through for the achieved questions, and we're focusing on the 2020 exam, and it's got, I think, 6 or 7 achieved questions in it, which will be a bit better than the 2017, 18, and 19 exams. So let's jump straight into question 4 from the website. Got it over there on the left. So the section of a spider web has 2 connecting right angle triangles, and we can see the right angles floating in down there. We've been told about angle PQS, which is down there, 63 degrees. We've been told about QS, which is 16.4 centimeters. We've been told about angle Q, we've been told about the right angles, we already said that. And then finally, QR, 7.5 centimeters up the top there. We've been asked to calculate X, which is the length from P to Q. So P to Q floating in over there. So I won't bother drawing another triangle for this one, just because the diagram is fairly easy to see. And I guess the main bit of information is I've got a side and an angle, which means I should be able to use trigonometry to find out that missing side. So let's label the sides. There's the hypotenuse. Down below, that's the opposite, and left over is the adjacent. We do not care about the opposite, which means we're dealing with cosine or cos. So let's got cos angle equals A over H. I'm now going to substitute. I know my angle is 63 degrees, so that's going to become cos 63. That's going to be equal to A, which is X, and H, which is 16.4. So X over 16.4. I'm now going to use a bit of algebra. So to get rid of that divide by 16.4, I'm going to go times 16.4, and I'm going to do it to the other side as well. When I simplify that, my X will be equal to 16.4 times cos 63. This is when you're going to grab out your calculator, and when you do all that, you're going to get to 7.45. Don't forget your units, centimeters, and that there had a 2dp rounding. Just a reminder, if you're not getting this answer from the above line of working, you might be in the wrong mode. The radians mode will not get your answer correct. You must be in the degrees mode. Now moving on to question 5. I'll leave my working from the previous question up there. But question 5 says calculate the size of angle Y or QSR. So we've got angle Y down the bottom there. And I've got a different color pen, but again, we've got a right angle triangle. We've got 2 sides. So we should be able to use inverse trigonometry to find out that internal angle. So the hypotenuse is over here. We do not care about that side of the triangle. The opposite is over here, and the adjacent is down there. We care about the opposite and the adjacent, so we're going to be using tan. So tan angle is equal to O over A. We now substitute tan Y is equal to 7.5 over 16.4. Now going to use inverse tan, so tan minus 1 of 7.5 over 16.4. Close that bracket there. When you put that into your calculator, I'm getting 24.58 degrees, 2dp rounding. Again, if you're not getting that, check your calculator that you're in the right setting. Now on question number 6, and it says sometimes holes can appear bigger in a spider web, and this here is representing the spider web. Below is part of it with a hole in the middle, points Q. All of these, they lie on the circumference of a circle, and we've been told about the angle down the bottom being 25 degrees. We've been asked to calculate the size of angle A, which is up the top there. So this is the first of the angle or the actual geometry questions as opposed to trig and Pythagoras' theory. So let's get into it. Don't forget our geometric reasoning. So the first step is this triangle here. That is sitting within a circle, so it's probably going to be an isosceles triangle. And that's because the radius over here and here is the same length. And that means this angle down the bottom and this angle, which we know is 25, they're going to be the same length because they are the base angles of an isosceles triangle. So let's jot that down. So that's CPR. So angle CPR PR, that's going to be equal to 25 degrees. And don't forget your reasoning. Base angles in an isosceles triangle are equal. Now that we've dealt with the base angles, we can use the rest of the triangle rule to find that angle sitting near the center of the circle. So that is angle PCR, and we know that's going to be equal to 180 degrees minus 25 minus 25. Those two minus 25s being the other angles in the triangle. And when I do that calculation, I'm getting 130 degrees. And my reasoning, internal angles in a triangle, they equal 180 degrees. So I now know this angle down here, sorry, not 180, but that's 130 degrees. And hopefully you can see what I'm drawing here, but we've got an angle that goes to the circumference, and you can see the arc along the bottom here. And then from the same arc, it goes to the center. And this is one of our circle theorem rules. So the angle in the center is twice as much as the angle at the circumference. So I know that angle, I suppose A, which will be equal to angle PQR, that's going to be equal to 130 degrees divided by 2, which is equal to 65 degrees. And really important, don't forget about your reasoning. This one's a bit awkward because there's no real short way to do it. But angles at the center of a circle are 2 times the angles at the circumference. So you may have a shorter way of abbreviating, that's awesome, but I sometimes struggle with the abbreviation, so I just write it out in full when I'm in doubt. So that wraps up question 6. Now moving on to question number 7. And I guess the key thing is we've got a regular pentagon, and we've been asked to calculate the size of angle X, and that's sitting over here. My starting point is I realize that angle X is sitting within an isosceles triangle, which means that down there is X. So I can find out X as long as I know this angle over here, which is the internal angle of the pentagon. So what I'm going to do, I'm going to start off with by calculating this, because all of the angles in that pentagon are going to be the exact same angle. So angle EDC, that's going to be equal to 180 n minus 2, so that there is the total internal angles of a shape. And because it's a regular polygon, I'm going to go divided by n. That'll chop it into even portions for each angle. So let's substitute now. So we're going to get 180, 5 minus 2. That there is divided by 5. 180 times 3 is 540. So we're going to get 540 over 5. And that there gets us to 108 degrees. So this here was based on 2 reasons. The first one, I'll just kind of write it up the top here. Internal angles of 5-sided shapes. 5-sided shapes sum to 540 degrees. So that's how we got the numerator there. And we divided it by 5 because the internal angles of regular polygons are all equal to each other. So we've got internal angles of regular polygons. They are always equal. So 2 reasons to get to that. So we've now found out this angle here is 108 degrees. And we're going to use the triangle and base angle of a triangle rule to find out the rest. So the math for that, so we know that X is going to be equal to angle DEC, which don't forget is also equal to angle ECD. So ECD. And the maths for that is we're going to start off with 180 because we are dealing with a triangle. We're going to take away the 108 degrees from the internal angle. And because the rest of the angle is shared between those 2 base angles, we're going to divide whatever that is by 2. So the numerator, that's going to become 72 over 2, and that there gets us to 36 degrees. And like the first rule, we did two things to get to that. The 180 minus, that was because it was an internal angle of a triangle, they summed to 180, and the divide by 2 part of it was because they were base angles of an isosceles triangle, so I need to get both of those down. So internal angles of triangle equals 180 degrees, and base angles of iso triangle, they are equal to each other. We are now on to question number 8, and we've got in a spider web. So this exam had a spider theme. ABC is a straight line. We know that AD is parallel to BE, and we also know that DB is equal to AB. So there we go. BD is equal to AB. And that tells us we've got an isosceles triangle as well. That information will be useful later. We've also been told about the angle down here, 64 degrees. Finally, calculate the size of angle P, which is sitting down there. That's EBC. So this one was a bit messy, but I started off with, these are my parallel lines, and this line here is a bisecting line, which means this angle here on the opposite side of the bisecting line is an alternate angle. So I know that top angle there is going to be 64 degrees. So that there is 64 degrees. So angle ADB, that's equal to 64 degrees, and that's because alternate angles, so alt angles in parallel lines, they are equal to each other. The next step, as I said before, we've got an isosceles triangle floating around here, which means that other angle down the bottom, so the base angle, also going to be 64. So down there, 64 degrees. So we've got angle DAB, that's going to be 64 degrees as well. And my logic, base angles in an isosceles triangle are equal. The final step, there's actually a few ways to kind of finish this question off. You could have calculated that final internal angle of the triangle and then use the straight line rule to find out P. But I'm going to go straight to P, and that's because if you have a look down here, there's my parallel lines. Here's my bisecting line, which means 64 and P, they are corresponding to each other. Doesn't matter which way you did, one's a bit shorter, but you'll get full marks as long as your reasoning's all good. So angle, P, because that's what we've been asked to calculate in the question, that's going to be equal to angle EBC, and that's going to be equal to 64 degrees, and that's because we've got corresponding angles in parallel lines are equal to each other. Number 9, a lot of information to this one. So we've got a spider web that's fixed to a tree just over here, and down here we've got a whole lot of information. So we've been told about a couple right angles. We've been told that SW is 120. We've been told that WT is 80, and finally we've been told about that internal angle down the bottom there. So messy diagram, and this diagram was more useful in the subsequent questions, maybe the merit and excellence ones. But we've been asked to calculate, or we've been asked to show the height of BT is this. So we've been asked to show that this here is 16.63. Just a reminder, these show questions, they give you the answer, and you must get to that same answer. So what I'm going to do is I'm just going to complete this triangle here just so you can see it a bit better. But I've got a right angle, and I've got a side with an angle, and I'm trying to calculate the side up here. Let's just call that X for now. So I can just use regular trigonometry to go ahead and find out that second side. So question number 9, pop that up there. This side here is the hypotenuse. That's the opposite. The adjacent's down the bottom. We don't care about the adjacent, so we're using sine. So sine angle is equal to O over H. I have an O value, so even though I know it's 16.63, I'm substituting an X because I'm trying to show that that's the case. So we've got sine 12 is equal to x over 80. I'm now going to go times 80 times 80. So x will be equal to 80 times sine 12. After that, we've got x is equal to 16.63 centimeters. And that there is a 2dp rounding, and we're a big fan of that because that's the answer that they've given us, so we've shown that that's the case. So this wraps up all the achieved questions from the 2020 exam. Hopefully you found them useful. There will be some merit videos coming up shortly, so make sure you keep an eye out for those.